So this is from last time. We had a reference mean of 90, standard deviation of 4, alpha 0.25, and 100, probably this directly from the textbook, probably from the 6, I believe. So we had two cases. One where was right at 91, the effect size was very small. We computed the power was very small, we didn't project. Then we moved on to a case where we have a really large effect size, the overlap is small, so we are going to project. And power in projecting is 98.24%. So I have to find beta. Beta is the probability of a type 2 error. I'm sorry. It is also the probability of a false negative. Writing both of them so that we can connect the two and make them interpret. Based on what we see from the picture, the power is 98.24. We got that using this shaded area. We use the calculator. It will include that part too. One of that. Okay. All of that. We used normal CDF to get a probability. I showed you how to do that using the calculator. 98.24%. The shaded area under the curve in black is 0.05. I also stress that when people sketch the graphs together, they end up shifting the real number line. You're not shifting the real number line. That remains fixed. What gets shifted is the curve. So here, the predicted value is high, 105. So shifts to the right, appropriate test, right tail test. Our conclusion last time was to reject the norm. Given this scenario, what is the probability of a false negative? So I want you to think about what a false negative is and tell me what we should put in these lines. We will start with this. If you need hints, we will play the word game to fill this up. So, what should go in there? Think of what a false negative means and try filling this too. Good job. Riley? What do you think?
I thought it was rejecting the null when the null was true.
So that is alpha, right? That is the probability of a false positive. You are rejecting the null when you're not supposed to. In other words, the null is true. Here, you don't reject the null or not rejecting the null when the null is false. In other words, alternative is more likely. How do we find that probability of the two? Which is the null distribution? This one or that one? The one on the left, one on the right. one on the left. Okay. Good. Great. When we found alpha, or when we fixed alpha, we used the black curve, or the curve in black, to find that area. We used normal CDF. It was approximately 0.05. It's 0.0495 something. We used this curve, null distribution, to get that shaded area. In other words, we assumed the null is true and found the probability that we would reject. Good. False positive. Now, if the null is false, which would mean I have to use the alternative distribution. Do you agree? The curve in blue. If I put the condition that the null is false, I can no longer use that. I should be using this. Good. Last time, when we found power, we used this one. My bad. In my mind, I thought I drew it in blue. I'm sorry. Both of them are black. We'll do one on the left and one on the right. But you get the picture, right? We pick the alternative, and when we pick the alternative, we use that value to find the power. If you go back and look at the definition of power, it is done under the condition that the null is false. So last time I wrote the probability of rejecting the null when null is false is power. So that's how we got the blue curve, or black curve, one on the right, shaded in blue would be power. Okay, maybe I'm going colorblind, but colorblindness doesn't work that way. Maybe just blind.
It's the 98.24% the blue
Yes.
portion and the black portion, yeah.
Yes, it's a full value. So this would be power, all of it from here. The shaded area here in black would be alpha. The difference is alpha is computed using normal CDF, but with the curve on the left. Power is computed with the curve on the right. Both of them will use normal CDF. Good. Okay. So null is false would mean I have to use the curve on the right. Not rejecting will mean I'm not going that way. I'm going this way. Yes. If the null is false, the probability of not rejecting the null can also be found using normal CDF. Null is false would simply mean that there is evidence toward the alternative, and the right thing to do will be to reject the null. Correct. So here we want to find the probability of not rejecting the null. So in using this picture, we have to come up with a value for beta. Again, beta is a probability, and it is the area under the curve. Yeah. So any thoughts on how we would compute that value? The easier way to get this answer is to remember that power is 1 minus beta, which means beta is 1 minus alpha. Oh, great. So this is 1 minus power. We already know what power is 0.9824 approximately. I don't know why professors hold these hands. I'm kind of guilty of that too. See, we're going to end up on that show TLC orders. Clear? So if I have to shade, I will be shading right there. Good. Now, in terms of interpretation, we are looking for a false negative probability. False negative in the means would mean you are sticking with the null when you should have rejected the null. So correct decision. So if you look in the textbook, I guess it's called decision errors. The error in making a decision, and we want to know the probability of that happening. We did alpha last time, it's beta this time. 1 minus power, 1.76%. The probability that you make the correct decision to not reject the null, in other words, stick with this, given that's what you observe. Good? That's me.
Wouldn't it be the probability of an incorrect decision?
It's correct. No. It is the correct decision.
Wait, incorrect?
Correct.
Okay.
So I'm going to get to it in a second. I wrote initially incorrect, but I changed my mind because this would be easy to interpret. So if I said, I am not going to reject the null, I'm going to stick with this, no matter what that 105 is. Good. I'm going to stick with this. Ignore that. Conclude mu is less than or equal to 90. According to the data, this is true. Correct. The null is false, which would be that part. That part. Agree? Yes. Yeah. Okay. So null is false, so I have to stick with the alternatives. If this is what I have for the second combination, and I stick with this, the chances that I made the correct decision to stick with this, not reject the no. Keywords being correct decision is only 1.76%. Good. So the chances that I'm right in not rejecting the no, given this is what I have, is 1.76%. So did I make the right decision of rejecting the no? Yes. Because if there is only a 1% chance, or approximately 2% chance, that I would be correct in sticking with the no, then that is not a good percentage. I agree. An extremely small boundary. So I should have rejected, or if I didn't start with the no, that decision is not going to be correct. Good. So keywords are making the correct decision when the no is false. It is a small probability, so the decision to not reject is not the correct decision. Because the probability of you being correct in not rejecting the no is about 2%, which would mean there's a 98% chance that I'm wrong. So decision to not reject the no, did I not reject? Not reject no is not the correct decision to make. You should reject the no. That is what's likely, which we accomplished last time. Power was 98.24%. We did acknowledge that we should be rejecting the no. We also looked at this picture and said, well, it's way far to the right. The effect size is large. We should be rejecting the no based on what we observed. So if I don't reject, then will I be making a correct decision? No. Which is 1.76%. But now do keep in mind the concept of finding beta power. We typically don't do it in real life because it could get confusing easily. In computer science, we call it hit rate, miss rate. Biostatistics, we call it sensitivity, specificity. Remember, UTI test strips, pregnancy test strips, COVID test strips. We call it sensitivity, specificity. The fields that use both type 1 and type 2 are typically medicine, computer science. In statistics, with hypothesis testing, we don't consider power and beta because they are pretty theoretical. You got to repeat stuff over and over in order to compute those values. Good example would be a test kit for a disease, let's say COVID. In order to identify sensitivity, how sensitive the test is, you have to give the virus to patients in clinical trials repeatedly, different people. Then you would administer the test strip and then determine how effective it is in finding a true positive. So you've got to repeat it over and over to compute beta power. So that's not what we would be doing in class, or in this course, because you're looking at one sample, correct? You don't have the flexibility to repeat it over and over. You have one sample. So this entire concept of beta and power becomes arbitrary. Okay? Which is why I mentioned this is something nerds like me would do. Good. So what do we stick with in making a decision? Long time ago, I said we fix alpha to come up with the conclusion for a test statistic. One of the reasons of many is this. Good. Because we have only one sample. Are we clear? Alpha, beta? Explain that look to me. I understand that look.
I had strep on Tuesday, so I wasn't here. So I'm kind of shaky about this, but if I have more questions, I'll probably just.
Right.
So it's more likely to get a type 2 error than a type 1 error? Because you say that's the way that you fixed it.
So I wouldn't say more likely, less likely. All I'm saying is we fix this for a test, and I come up with a statistical procedure, just like you come up with a test strip that gives me maximum power, a power of 1. In other words, if it's positive, it picks up as positive. Because the only way I could get perfect true negatives and perfect true positives would be beta and alpha are 0. In real life, that's not possible. So we fix this and come up with a test strip, a statistical procedure that would increase the power to 100%, make type 2 error probability 0. So
I'm sorry, what was the difference between beta and alpha?
beta is type 2 error probability. Alpha is type 1 error probability. So alpha is the probability of a false positive. Beta is the probability of a false negative. So
Because I know they're both like areas under the curve, so it just depends on the error.
yes. These are probabilities and we compute them using area. Are we good with all of this? So when we proceed, we're about to see chapter 7, we're not going to be looking at beta and power. If you read articles, real life articles, they're not going to report beta and power. Good. Before we end, what are the things that would affect power? Sample size. If the sample size gets too large, it will change power. Effect size, standard deviation, those things will increase power or decrease power for a given test. So there are several important factors that one must consider prior to coming up with a statistical test. And those are beyond the scope of this class. So you just have to know that things like standard deviation, sample size will affect beta. Justin?
I just wanted to say that that was a question of when we were asking what affects like power.
A bit sample size.
Yeah, it mentions sample size and
Standard deviation. Yes. So that's simply a vocabulary kind of question.
Yeah.
There is no need to get too much into it. Will only confuse you because there are multiple combinations that I can show. Like, keep it simple.